So in the previous video, we looked at finding the general solution of a differential equation that initially didn't look like it was separable. As I mentioned, if we tried to expand by multiplying through by dx, we'd have difficulty isolating dx with x and dy with y. That would be kind of tricky. So we made this clever substitution. We said if we divide through this equation by x, we can create dy by dx as some function of this variable, this blended or hypervariable, whatever you want to call it, y over x. And then we said, okay, we'll let y over x represent u. So u is this replacement variable for this. And what followed from that was that y is equivalent to u times x. So what we had to do was substitute for everything in this equation. That means that the y over x becomes u, and the dy by dx is found by taking the derivative of ux, which by product rule is u plus x du by dx. So we said y was equal to ux, we differentiated both sides, and this became u plus x du by dx. With that substitution, we were able to separate variables and get down to this solution down here at the bottom of the video, and that's sort of where we left off. What I didn't do was leave off a follow-up question that you could do. So I wanted to suggest this one. You might want to try this one on your own. dy by dx is 2x plus 5y over 2x minus y. Now, to tackle this question, once again, we're going to try and create that y over x variable. And that's easily done if you divide the top and the bottom through by x. And it turns into this. dy by dx is 2 plus 5y over x and 2 minus y over x. When you do that, once again, we're going to use that same replacement of u being y over x. And so in doing so, we create u being y over x, y is ux, and we have that same dy by dx equaling u plus x du by dx. Now, when you do all the substitutions in here for the u's and the dy by dx, you have a relatively challenging separation to perform, and you're going to run into some integration by partial fractions. So just a heads up, you have to do it by partial fractions, and then there's a little bit of algebra at the end to get down to a final answer that looks like this. You'll get y plus x all cubed is some arbitrary constant times y plus 2x to the 4. So I sort of challenge you to try that, give it a shot, see if you can get to that answer. But now I want to look at what happens when the y over x function can't be created. So I've given you one like this, where I say find the general solution of this derivative, this differential equation I should say, where dy by dx is x plus y squared. So instead of a y over x substitution, what I'm going to do is I'm going to let, as a substitution, I'm going to let u equal just plain old x plus y. Or in other words, y is u subtract x. Well then, that will be easy enough to replace u in here as well. Over here, I have to replace dy by dx. So dy by dx will be du by dx minus, and the derivative of x, of course, is 1. So what does my equation turn into? When I make those substitutions, dy by dx equaling x plus y squared turns into du by dx minus 1 equals, replacing x plus y with u, that's u squared. So what do we have here? We have du by dx is u squared plus 1. Super easy to separate the variables now. We have 1 divided by u squared plus 1 du equals dx. And so now if I integrate both sides, we're almost finished. What do we have here? when I integrate this side here, hopefully you will recognize that that is nothing more than the arctan antiderivative, or tan inverse antiderivative. So that's tan inverse of u. And on the right-hand side, we just have x plus some arbitrary constant. So what do we take from that? We have that tan, replacing the u with our x plus y, tan x plus y, tan inverse x plus y is x plus c. And if you want to get that explicit in terms of y, you would say x plus y is the tangent of x plus c, or y is simply tan of x plus c subtract x. So that's another type of substitution we can consider. So we took wholesale the x plus y and replaced it with a single variable in this problem, and that actually made everything nicely separable. So we're always trying to create that separable situation. So we took out the x plus y, made it u, y turned into u minus x, dy by dx is then du by dx minus 1. And with those substitutions, we get into a situation that is pretty easily solved. So that sets us up for a much more difficult question that I'm going to do in a third video.